Dave Sutton, expert survivalist, and I'll show you what it takes to build a working cell phone charger out of scratch. So first, if you come over here, I'll show you the first step in building a working power supply. Right this way. So first off, when you're using voltage that comes from a wall, you're going to be getting a sinusoidal wave which looks something like this. It's constantly changing, snaking up and down between positive and negative as it swerves through this wave line. But what we need to charge an iPhone is a nice flat line. This is called DC, or direct current. It's flat and it's stable, and it's exactly what we're looking for. But it's going to take a lot of work to get from this to this. The first stage is to bring this level down to what we need, because when we get voltage from the wall, it's going to be at around 110 volts in the United States. So in order to bring this down to what our iPhone needs, we're going to use a device called a transformer. And a transformer consists of coiled wires that conduct voltage through electromagnetics. And so when we send the voltage through the transformer, it's going to go from a nice, large, unusable voltage like this to a smaller wave like this. It's still going to be in a wave form, but at least it's going to be smaller, closer to what we're looking for. Since no transformers were available, I'll have to improvise. By carefully winding the wire into the correct number of turns, I can control the voltage and step it down to the level that I need. So you've already seen how we've taken this wave form that's coming right from the wall, and we've used a transformer to step it down to the voltage level that we're looking for. Now the problem is, we still have this wave that's fluctuating up and down, positive and negative, and that's not going to work for our job. What we're going to use is a part called a diode. Now a diode only allows current to travel through it when there's positive voltage. So right here, this is our waveform. And what the diode will do is the diode will let us only keep the positive top part of the wave. So we'll have this positive part, and then a gap, and then another positive part, which is more like what we're looking for. But the problem is we have these gaps in here. A more efficient form is to use something called the full wave rectifier. And this diode bridge will allow us to keep the entire wave in the positive form. So instead of this wave snaking between positive, negative, this time it'll all be in the positive section. The next part of our assignment is to find the diodes. Thankfully, we came to a technical college, which means it's going to be easy to forage for parts. In fact, I see an excellent part source right over there. Got to be quiet as we sneak up on it. The trick is to just quickly slit the power cord, and now it's as good as dead. I'm just going to get my knife in there and skin the beast. And inside, you just have to reach through all these intestines to pull out the parts you need. And always remember to make full use of the parts. So don't let any part of the PC go to waste. These diodes are exactly what we've been looking for. Right now, thanks to our full wave rectifier, we've got this voltage waveform where the voltage forms these hills. And it's still staying in the positive region, but it's making these hills, which is not good enough for us. We want that nice straight line. And one way that will get us closer to that is by using a part called a capacitor. Now a capacitor acts kind of like a battery. It will charge up and then gradually release its charge over time. And by using the capacitor, we can now see this output is what you're going to get, where it'll charge up and then gradually release it, and then it reaches the next hill, and then starts to release the charge, charges up a little bit, releases the charge. And this is much nicer than the hill-like waveform we have over here, because it stays mostly around a set voltage. It's not perfect, but it'll get us pretty close to our goal. There are no capacitors around here, so I'll need to order the part online to finish my power supply. This is gonna take a while for the capacitor to arrive. It's about time I need a shelter. Right here I've set up the perfect survival shelter for this environment. I've got this tarp to keep out the rain, and then underneath this protective lab bench, I've got my sleeping bag where I can spend the night as I wait for the parts to arrive. I've made my shelter, and now I'm getting ready to make a fire to provide warmth for the long wait ahead. It's been 5 days. According to UPS shipping tracking on our capacitor, it looks like it'll be coming any day now. And just in time, too. 2 members of our camera crew have already passed out due to boredom. You'll die from dehydration far faster than you will from starvation. Now here, in this barren wilderness, it can be difficult to find a supply of fresh drinking water. Up here, I've set up my bandana to hope that I could catch some water. I'm going to climb up and see if maybe just a few drops of water might have dripped from the ceiling. It may not be much, but my bandana captured just a little bit of water, a few drops that I've so desperately sought for. When you're in the wild, you just have to take every bit you can get. The day I've been waiting for has finally arrived. Today, UPS delivered this package containing the capacitor vital to finishing my power supply. Let's cut in and find what we have. Just the part we've needed. I haven't eaten in 5 days, and right now, these packing peanuts are looking very appetizing. When I start to put this into the circuit, it's important that we test to make sure that we have the right capacitor value. So over here we've got specialized lab equipment, which is just perfect for testing these things. But sometimes in the wild you're not going to have access to lab equipment, so you have to find alternative means of testing it. So to test to see if this has a charge, I'd say it carries quite a charge. Let's put this in our circuit. Right now, this is an image of what the output from the power supply with the capacitor is going to look like. As you can see, as the capacitor is charging up and discharging, it's creating a little bit of a ripple voltage. Now, the ripple voltage is much better than the output from the full wave rectifier, but it's not good enough for our power supply. We really want something that's going to have a nice flat line like this, where we get a solid voltage reading. And the best way to achieve that is to take our ripple voltage from the capacitor and put it with a Zener diode. Now, a Zener diode is a special type of diode designed to be used in reverse bias, which means that you put it the opposite way that it would normally conduct, and therefore you get a constant voltage. Right here, I've created the working circuit. Now, it may be a little difficult to see how the circuit fits together because of the way it's connected with the breadboard. But from here, I've now connected it to the oscilloscope, which is a device that lets me manually view what the output's going to be. So here you can see we've got this nice straight line, exactly what we need to charge my iPhone. Well, it seems like our quest has finally come to an end. Using basic electronic parts, we've found how to build a working DC power supply. By using a transformer, we've found a way to bring the voltage down to the level that we'll need. By using diodes in the form of a full-wave rectifier, we've been able to keep our DC portion of the wave. And then finally, using capacitors and a Zener diode, we've smoothed that out into a line that's stable enough for me to charge my iPhone. And it's just in time. I've almost drained the entire battery filming this video.